Welcome back, everybody. I decided to give myself July 4th off yesterday, but today we're going to be talking about Hecke Correspondences from the moduli-theoretic point of view, because the way we developed Hecke Correspondences last video was somewhat abstract, and I think this way of thinking about them is a little bit easier. So we're going to utilize the divisor group here. Let's let W be a set. Let's let div W just consist of finite formal sums of the form sums over points in W n sub p times this kind of formal object parentheses p. In other words, it's the free abelian group on points of W. These np's here, they're just integers, and I need all but finitely many of them to be 0. Okay, and this parentheses p here, that's a formal symbol that just represents the point p in W. Okay, so let's let k be an algebraically closed field. Let's let x be a smooth projective k curve whose set of k points is denoted x of k. We're going to use this notation a lot. Let's let t be the triple z phi psi. That's just going to be a correspondence on x, defined last video. We'll denote also by t the following map. It'll be a map from the k points of x to the divisor group of the k points of x, and it'll send a point x in x, if you like, to the sum over z and z, such that phi of z is x, sum of what? The ramification index of phi at z times the formal point psi of z. So you have this going on. You have z going to x via phi and also via psi. What you're doing is you're taking a point little x and big X here. You're looking at all of the points in z that map to it under phi. You're taking psi of all of those points. You're making formal symbols out of those, and you're weighting each one by its ramification index, its phi ramification index, not its psi ramification index. Okay? And so what this setup, this kind of complicated setup is going to allow us to do is to very concretely get a hold of the Hecke action or the Hecke correspondence moduli theoretically. Okay? What I want to do is I want to know what's a formula or what's a way of thinking about this if T is the Hecke correspondence T sub p defined last video. So let's say x here is, one of your modular curve x sub 0 of n. Okay, and k is the complex numbers. What is an actual formula for the Hecke correspondences if you set them up like this? Well, let's let E over k be an elliptic curve where k is still your algebraically closed field. Let's let L be a subgroup of E of order p for some given prime p. We'll denote by E mod L an elliptic curve, which is the image of a separable isogeny with domain E and kernel L. So usually we would write it like this. Okay. E over L would be the image of some separable isogeny whose domain is E. What is a separable isogeny? Well, remember, an isogeny of an elliptic curves like this induces an inclusion of function fields going in the other direction. If that inclusion is just a separable extension of fields, then we would say the isogeny is separable. Okay. We know E mod L is unique up to isomorphism. We talked about that in a previous video. Okay, let's take lambda from E to E mod L, a separable isogeny with kernel L, like we just discussed. And let's let C be some cyclic subgroup of order n for some n. Okay, so C lives here. Intersecting L trivially. Now, if the GCD of n and p is 1, this always happens by basic group theory. But if the GCD isn't 1, then okay, just pick C, like I said. Just make sure it intersects L trivially. Okay. The point is we have a well-defined isomorphism class given by the class E mod L, C plus L mod L in the set of k points in S sub 0 of n. And remember, S sub 0 of n is the set of all enhanced elliptic curves for gamma sub 0 of n. And this of k here means I just want to take the classes that are defined over the field k. Okay, what is this class? Well, what should it be? What is E mod L? It's just lambda of E, right? It's the image of E under lambda. And what is the C plus L mod L? Well, it's just the image of C under lambda. Okay. And the point is, what I mean by this class is well defined is that this class is easily seen to be independent of the choice of lambda. If you pick another separable isogeny E to E mod L, and you form, well, let's call it lambda prime, and you form the class of lambda prime of E, lambda prime of C, it's the same as the class of lambda of E, lambda of C. Okay. Okay, perfect. How about if we do things with points instead of subgroups? Well, similarly, if you take a point P and E of order n, such that the group generated by P intersects L trivially, then we have a well-defined isomorphism class given by the class of E mod L, P plus L, and S sub 1 of n, its k points. Okay, what is that class? Well, the class of E mod L, P plus L, is of course just the class lambda of E, lambda of P. Okay, so you're taking lambda of E again here, and then you're taking a point P in here of order N, and you're looking at its image, and you're just calling those images E mod L and P plus L. You're using coset notation, basically, is what's going on here in both cases. Okay, and again, this is independent of lambda. Okay, so here's the big theorem of the day, theorem 3. Let's let E over Q adjoin J be an elliptic curve with J invariant J, like the universal elliptic curve over Q adjoin J, for example. Let's let S, S prime, and S double prime be subsets of the complex projective line containing all places where E has bad reduction and satisfying the following technical compatibility condition for the correspondence. I want phi sub P inverse of the S complex points of X sub 0 then to be contained in the S prime complex points of X sub 0 of NP. And I want psi sub P of the S prime complex points of X sub 0 of NP to be contained in the S double prime points of the complex, the S double prime complex points, excuse me, of X sub 0 of N. So remember, we have this Hecke correspondence, right? It's two maps, phi sub P, psi sub P from X sub 0 NP to X sub 0 N. I want to make sure that if I grab a hold of the S complex points here and look at their pre-image under phi sub P here, that's contained in the S prime complex points here. In other words, I want compatibility, okay? And then I also want to make sure that when I take psi of the S prime points here, psi sub P of the S prime points here, that I end up in the S double prime point complex points here. I want all these sets to match up in a nice way, basically. Okay, now let's let P be the second element of a Z mod NZ basis for the N portion of E. Let's let C be the group generated by P. It turns out the following commutes. Okay, so I definitely have the usual Hecke correspondence from the S complex points of X sub 0 of N to the divisor group of the S double prime points of X sub 0 of N. Okay, so basically this map here is what I described at the beginning of this video. Okay, because we already have the Hecke correspondence, and we know we can think of correspondences in terms of divisor groups from the beginning of the video. So this is like the new map of the video today. Okay, what's this left arrow here? We've already seen this left arrow. It's the restriction of the isomorphism of the complex points of X sub 0 of N without the S to S sub 0 of N of C to the S complex points of X sub 0 of N. We've seen the map before. It sends X to the equivalent to the class of E sub X, C sub X. Remember, E sub X, C sub X are the reductions of E and C mod X, respectively. Okay, what's this right arrow here? Well, look, I mean, every map of curves like this is going to induce an obvious map on divisor groups. I'll let you think about that. So this map here, this right map is just induced by the left map. Okay, so the question is, what's this magic bottom map here that commutes this diagram and allows me to think of the Hecke correspondence, not just kind of Galois theoretically, but actually moduli theoretically. Okay, well, it's actually a pretty understandable map. What it does is it takes, I mean, what are elements here? They're complex, they're enhanced elliptic curves over C for gamma sub 0 of N, right? Okay, so what's the map? It takes a complex enhanced elliptic curve, E comma C, and it sends it to the following sum. It sends it to the sum over all subgroups of the P torsion of E of index or order P. They're the same because E sub P has order P squared, right? But I also want to make sure I'm not just taking subgroups L that satisfy that are order P in the P torsion of E. I also want to make sure that when they intersect with C here, they do so trivially. Okay, and what am I summing over? I'm summing over the complex enhanced elliptic curves E mod L, C plus L mod L. So what's going on here? It's very simple. You're taking a complex enhanced elliptic curve for gamma sub 0 of N, equipped with the N torsion data C, and you're saying, what are all of the images of this elliptic curve E under separable isogenies whose kernels, we'll call those kernels L, intersect C trivially and have index / order P in the P torsion of E. Find all of those, make their classes, and add them up. That's all you're doing. Okay? And the same idea works if you replace x sub 0 of n by x sub 1 of n, s sub 0 of n by s sub 1 of n. I mean, what should you replace this left arrow by? Well, you're not going to send x to excx. You're going to send x to expx, okay, where p is a point of order n now. And what would the bottom arrow be replaced by? It would send an complex enhanced elliptic curve for gamma sub 1 of n, which we'll call e comma p, to the sum of what? Over what? Well, again, you'll take all subgroups L of index / order p in the p torsion of E, but you're going to make sure that when you take L and you intersect it with the group generated by P, that intersection is trivial, and you're going to add up all the classes E mod L, P plus L. So again, you're taking your elliptic curve E, you're looking at all images of it under separable isogenies that have kernel an order P subgroup of the P torsion of E, which we'll call L, but you just want to take the ones, you just want to take the L's that intersect your given n torsion data P, or more specifically, the group generated by it, trivially. Okay, so I think this is a kind of a very nice way to think about the Hecke action. The proof of all this is in Cornell, Silverman, Stevens, chapter 3. But yeah, I mean, the usual Hecke correspondence to me is a little bit hard to remember and intuit, whereas this is one of a few ways we'll look at that makes the Hecke action pretty natural. Okay, so next time we'll look at the Hecke correspondences orbit theoretically, or congruent subgroup theoretically.